In this video, we want to focus on how to use the interaction equation for timber column. And so we're going to start with a stud wall. I'm just drawing one particular stud there. We'll assume they're 2x6 studs. However, this is a whole wall that goes into and out of the paper, so these would be spaced at a 16-inch spacing. And we'll assume that the grade of these studs is actually stud grade. You'll notice that I've drawn at the very top of the load, or the very top of the wall, a uniformly distributed load acting along the top of the wall, so it's 2,000 pounds per foot. But because of the 16-inch spacing, note that it's not necessarily 2,000 pounds acting on each stud. We'll go ahead and adjust that here in just a moment. Also note that this wall is capturing a wind load of 15 pounds per square foot, and this would be an area load. Even though I've drawn it as a uniformly distributed load, this would be an area load acting along the entire length of the wall. And so we'll also adjust for that as needed. First thing I want to do in this problem is go ahead and find my factors that I need. And so we'll go ahead and we'll call it design factors. And I need to go and pull some values from some of the tables. And so from the supplemental table that is posted online, we want to pull the allowable compressive stress and the allowable bending stress and the modulus of elasticity for this particular grade of studs. And so if you go there, you'll find out that for a 2x6, which is of course dimension lumber, using the stud grade line, F sub B equals 700 psi, F sub C equals 850 psi, and the modulus of elasticity is 1,400,000 psi. And again, that comes from the supplementary table that I've attached. Next thing we want to do is come up with our adjustment factors. And so we go to the size adjustment factor table, and for a 2x6 in the bending category, you'll find that the C sub F equals 1.0. Make sure and notate that's for the bending. C sub F, the size adjustment, also equals 1.0 for F sub C. Those can be found using the 2x6 line item. So I think the line in the table says 5 and 6 inches for stud grade. And so we just need to make sure we're on the right grade section there. If you go to figure 9.23, we can pull the duration adjustment, and for wind we discover that it's 1.6. And so this is for wind from figure 9.23. All these other factors are from the supplemental tables that I posted. Okay. We are ready to start solving this problem. I'm going to erase, and then we'll break it down into a 4-step process where we want to solve these following terms. We want the There we go. Sorry, wrong color. We want to find the allowable compressive stress and adjust it. And then we would need our actual compressive stress. We need our allowable bending stress adjusted and our actual bending stress. And those are the five, I can't even count. Those are the 4 different parameters that we want to actually find to plug into the interaction equation. I'm going to erase now, and we'll solve each of those 4 factors and then plug them into the equation. Okay, I want to solve the allowable compressive stress first, partially because this is the most complicated of the four factors to come up with, and also just because it's a good one to start with. So this is no different than what we did on our previous homework assignment. Recall that we've identified that this particular wall, because it's a stud wall, I'm going to define this and make the assumption that it's load bearing. And because it's load bearing, the nails and the sheeting that would be the particle board, the OSB, that would be on the outside of this particular wall would actually brace the weak axis in multiple points. And so the assumption we're going to make, because this wall is load bearing, is that the strong axis will actually govern. So rather than check a strong axis and a weak axis, we'll just make that assumption. We want to check our L over D ratio for the strong axis. Of course, the strong axis would use the full height, 11 feet. We would adjust that, convert it to inches, and we would want to use the strong axis dimension. This ends up being the larger value for a 2x6 wall. And if we run that math, we discover that L over D, or my slenderness ratio, is 24. Next, we want to calculate Euler's critical buckling stress. So F sub CE is equal to KCE times the modulus of elasticity all over L over D squared. KCE, you'll recall for sawn lumber, is 0.3. I think it's 0.418 if it's a glue lamb, but we're using 0.3. I think this comes from page 477 in the textbook. Don't quote me on that page, but you can refer back to it as needed. 1,400,000 psi, and the L over D ratio of 24 squared. You run that through, and we end up with our calculator indicating that the Euler's critical buckling stress is 729 psi. Next, we want to calculate our adjusted compressive stress. When we did this previously, we grabbed the value from the chart, applied the duration factor. Today we want to make sure that we're also including the size adjustment. And so F sub C from the chart, this is the Douglas fir chart for a 2x6 stud grade. We found this on the previous page. 850 psi for the allowable compressive stress. The wind load duration was 1.6, and the size adjustment for the compressive stress was 1.0. And run that through our calculator, and we end up with 1,360 psi. Next thing we want to do is take the ratio of F sub C to my F sub C star. So simply 729 psi. I usually solve them in that order because that's the order we do the ratio in. 1,360 psi is the denominator, and I discover that that ratio is 0.536. Once we have that, we then want to go to table 9.3 in the textbook, and we'll interpolate between 0.53 and 0.54. Make sure we stayed in the sawn lumber category, and we discover that the stability factor for this column is 0.458. And we'll just make a quick note here that this comes from table 9.3 for F sub CE over FC star equals 0.536 and sawn lumber. Make sure you know how to read that table. Sometimes when you're watching a video or watching me do it in class, you think, yeah, I got it. But pull your book out, make sure you can get the same number that I did so you know how to read the table. Final thing, once we've got the column stability factor, is simply make the last adjustment. Take our initial adjusted value, multiply by the column stability factor, and so we end up with 1,360 psi times 0.458, and we find that the allowable compressive stress, of course this is the adjusted allowable value, equals 623 psi. That's one of the values that we want to use in the interaction equation. So let's hang on to that value, jot it down. We'll come back and grab it here in a little bit and plug it in the interaction equation. I'm going to spend a few seconds erasing, set up to solve the next couple steps, and then we'll come back. Okay, next thing we need to do is calculate our actual compressive stress. Now that we've got our allowable value on the actual, so that we can take that ratio in the interaction equation and run with it. So you'll recall that actual compressive stress is simply the point load divided by the area. And so I've got the point load first. It's 2,000 pounds per foot acting along the top of the wall, but recall that the stud spacing is every 16 inches. So we want to take the 2,000 pounds per foot and we want to adjust that for the spacing. And so we'll go ahead and multiply it by 16 inches. The 12 simply converts it to feet so that they would cancel out. And I discover that I have 2667 pounds acting on each stud. Of course, if the spacing was only 12 inches, then there would be 2,000 pounds acting along each stud. And so the spacing adjustment makes sure that we're accounting for how much of that load is acting on each stud and accounting for that difference in there. So spacing factor. The actual compressive stress, F sub C, then is equal to the point load divided by the area. So I got 2667 pounds. We can go to table A1A in the textbook, and for a 2x6 we find that the area equals 8.25 inches squared. So table A1A, and run that math through our calculator, and I find that my actual stress is 323 psi. So there we go. There's another one of our factors that we will need to plug in our interaction equation. I'm going to just keep scrolling down and we'll keep solving here. I think we're in a good spot. Let's next do the allowable bending stress. This is the baseline bending stress multiplied by all the adjustment factors that we have required. And so for this problem right here, I've got FB prime is equal to my baseline value multiplied by my duration factor multiplied by the size factor. So we had these written out previously. 700 psi came from the supplemental table that I provided to you. A duration factor for wind load of 1.6 and a size factor for bending of 1.0. Run all that through your calculator. We discover that this value, allowable bending stress, is equal to 1120 psi. Final factor that we need to determine this is the actual bending stress. This is where we look at the load that is acting alongside of the column over here, the 15 pounds per square foot of wind load, and what kind of bending is it causing those studs to have take place in the lateral direction. And so first thing we need to do is determine what the uniform distributed load is. So we're an area load right now of 15 pounds per square foot. So recall that to get the uniformly distributed load, we do the spacing, in this case 16 inches. We'll go ahead and throw a 12 in there to convert it to feet, and we multiply by the 15 pounds per square foot. So this is the tributary width multiplied by 15 pounds per square feet, 8 inches from each, halfway between each stud, contributing for a total of 16 inches, and that accounts and makes it a 20 pound per foot uniformly distributed load acting along each of those studs. Next thing we need to do is simply calculate the moment. Moment for a uniformly distributed load is equal to WL squared over 8. If you didn't remember that, you could go to the common shape solutions and look that up for a uniformly distributed load. 20 pounds per foot is my W. My length is 11 feet. Of course, we square that, divide by 8, and I find out my moment is 303 foot-pounds. That's how much bending is occurring in there. Final thing we need to do is convert this to our actual bending stress. Recall that FB equals the moment MC over I, or we could also substitute in and note that that moment equals, actual bending stress equals the moment divided by the section modulus. The section modulus in this case, we can grab, I'm going to highlight this right here. If we go to table A1A, it shows the section modulus for the strong axis. But because we made the assumption that this is a load-bearing wall and the strong axis will actually govern the failure, then we can go ahead and use that value rather than have to calculate it from scratch. And so in table A1A, we discover the section modulus is 7.58 inches cubed. Of course, on the top we've got 303 foot-pounds, and we multiply that by a factor of 12 to make it inches, and we find our final factor is 480 psi. All right, now we have those four factors. I've got my F sub B, my capital F sub B prime, my little f sub c, my capital F sub c prime. Note also during the process we had that Euler's buckling factor F sub ce. Those are the 5 values. I didn't actually underline the F sub ce earlier, but this is also one of the numbers I need to pull. So you can go back and rewind and grab that value if needed. Otherwise, I'm going to erase and we'll throw everything into the equation and finish this problem up. Okay, we're back. We're ready to plug everything in. Let's make sure that we've got the interaction equation written down here as our starting point. So the interaction equation is my lowercase, my actual compressive stress divided by my allowable compressive stress. And for the timber equation, this is squared, plus my actual bending stress divided by my allowable bending stress. And then we have this last factor that accounts for the P delta effect. And it's simply a function of 1 minus the actual compressive stress divided by that Euler buckling. And all of this has to be less than or equal to 1. It's pretty easy at this point in time. I like to write things out and keep track of it separately, but we just start plugging our values in that we've already solved. 323 psi divided by 623 psi, and of course we square that. And then I end up with 480 psi as my actual bending stress, my allowable bending stress, of course that's adjusted, 1120 psi, and this inside this little thing, 1 minus the compressive stress actual divided by my Euler buckling stress, 729 psi. Again, that one was found halfway through the compressive stress equation. All of that has to be less than or equal to 1. I actually like to solve the left side of this separately than the right side. So if we were to plug this ratio in and square it, and then it was 0.269 on this side, and then on the right side, plug all that into your calculator, and it was 0.770. Essentially, it means as far as compressive stress is concerned, we're about 27% of capacity, and as far as bending stress is concerned, we're about 77% of capacity. If we add all that together, we discover that I'm 104% of capacity. This is not less than or equal to 1, or in other words 100%, and therefore with regard to bending and compression, this column is not adequate. Again, just as a quick summary, the left side of the equation shows that with regard to compressive stress and with regard to bending stress, when those two act in combination with each other for timber, for this particular loading scenario, that this is not adequate, and we'd have to either reduce the loading on there or opt up for a larger sized member. There's other ways we could do this by possibly bracing in the strong axis or some other things like that. For this homework, I'm not asking that you go through and give me particular scenarios as how to fix this. For the sake of this homework, we're just simply calculating whether or not it's adequate. However, you should be able to talk generically about what's happening and what our options are. So that's the process of the interaction equation. 4-step process, plug it into the equation and you're done. Hopefully this video has helped you out and you're able to solve the problem.